Okay, so hi everybody. Uh, for this video, we're going to talk more about geometric optics, lenses and actual mirrors. This is kind of developing on what we talked about in previous videos, where we basically looked at the basic rules for how light interacts with matter under geometrical optics. And in those cases, we considered flat surfaces and how light either reflects or gets refracted by interfaces. And in all those cases, we considered flat surfaces because that's the simplest geometry. Now we're going to start to consider the curved surfaces of lenses and mirrors that often act in optical elements and things like telescopes, microscopes, etc. Now, in this case, we're still going to be working in geometric optics in the sense we're going to still consider the case that these surfaces are relatively smooth. That is, at any given location on, say, a mirror or a lens, the surface is flat enough that you could say, okay, the angle of incidence equals the angle of reflection, or the angle of incidence has the appropriate interaction with the angle of refraction. The trick is, since different light rays will strike the surface in different ways, what happens after they bounce is variable. This can cause light rays to potentially converge onto a focal point or diverge. Now, this is an old field. People have been doing this for hundreds of years, and it has its own language, often expressed in terms of a variety of its own parameters, including focal length, image size, magnification, and so on. And these are worth knowing, but often in a lot of problems or places where this is dealt with, there's a lot of let's define a bunch of parameters, and it's not clear exactly why you're doing all of this. So before we get into actually talking about what mirrors and lenses do in terms of things we can mathematically describe, I want to motivate why we care about things where we can get rays converging or diverging. And this is my own personal take on this. You can find different takes in different sort of books. So what is important about these various things is they allow you to make images. They are the basis by which we make telescopes, microscopes, and how our own eyes work. And to get a very gross picture of how this works, it's useful to consider kind of one of the more fundamental parts of an optical instrument. There is some element in these optical elements that is responsible for detecting light. This is the fundamental thing we think about a lot. It's the retina of our eye. It is also the CCD chip or some electronic component in modern cameras, or film if you're really old. And the thing is, just having something that detects light is not enough to produce images. For example, say we just had a detector sitting out in the open, and we had two light sources, one red, one blue. Well, blue light falls everywhere and red light falls everywhere. Just by looking at the signals from the detector, you couldn't figure out whether there was one light that was red and blue, or two lights, or how far apart they were. There's no way to create an image with just a piece of material that detects light. You need something in between the light sources and your detector to actually make an image, to distinguish sources from different locations. Now, the simplest way to do that is with a hole. That is, you basically block out all of the light except one coming from a tiny little hole. In this case, only light from the red source can reach this part of the detector. Only light from the blue source can reach this part of the detector. So you would actually be able to distinguish those two sources and create an image. This is the basis of what are called pinhole cameras. And this works. For those of you who were around during the eclipse, if you looked at the shadow of trees on the ground, you would see images of the sun, which during the eclipse look like little crescents. So this works, but it's highly inefficient. very little of the light that is available to you reaches the detector. So this is why when you use pinhole cameras, you often have to have a really dark space so you can see the light coming through this tiny hole. What lenses and mirrors, or lenses and curved mirrors, allow you to do is do this more efficiently. Again, we have a detector, but what the lens or other optical element does is it allows light from on a variety of paths to end up in one place in the detector. Not just this light following a straight line path, but also light going up, light going down. And that's true for multiple locations. So in this case, we don't just have one beam of light getting to the detector, we have light coming from a range of positions. This increases the efficiency of this, and so you get more light hitting your detector, which is good. It also, as we'll see maybe on Friday, this also helps you get better images, not just brighter ones, but ones that actually can resolve more detail. So that's the basic reason this is important. We're trying to figure out a way to manipulate light so that particular sources end up at particular locations. That's a basic thing behind a telescope. It's a basic thing behind any camera. It's the basic way our eyes work. And that's why we care about this particular thing. It's a fundamental way we interact with light to be able to understand things. And this is happening in our heads all the time. So this is why we care about this. Now the question is, we do need to define things to understand what are the ways one can make this work. What are the limitations on, say, how big our detector has to be, how far it has to be from the lens or the mirror. These are, very fundamental questions. And what the world of geometrical optics often does is just try and figure out ways to figure that out fairly efficiently. And there are, again, its own language. I'm not going to be too picky on that, but there are some concepts that are important. One of them, which is very fundamental, is something called the focal length, or the focus, and the focus. So the idea behind this is with certain types of lenses, light rays that are parallel to the axis of the lens, however that's defined, will all converge on a point. This is an example from the textbook. So light going along the axis stays going along the axis, light a little above, hits this surface, gets refracted, hits this surface, gets refracted again, and then gets pulled down towards the focus. Down here, the light ray gets bent up towards this point, and all of these rays and anything in between passes through a single point called the focus. Now, these kind of parallel beams of light are what you get if you have a light source that's very far away. This could be sunlight. Sun is very far away, and so the light from the sun tends to come from the same direction. And so this is the point where all the light from the sun that's captured by this lens would be concentrated. That's why it's called the focus. Now, just to say, this doesn't have to happen. You have to pick a shape to the lens to ensure this happens. But that's not too hard to do. It turns out being close to a sphere does that pretty well. But what we're talking, so first of all, a lens doesn't have to have a focus. It often does because we want to use these practically for things, but there's no reason a random chunk of plastic or glass would necessarily have that. But so what we want is a thing that does that, in which case the critical parameter is this thing called the focal length, which is basically how far this focal point is from the center of the mirror. And to be clear on this, It is defined by how far in downstream from the lens it is. So this can be for a lens or for a mirror. But in this case, it's how far downstream from the lens it is. This distance turns out to be the fundamental property that defines how images work for this lens. Now, what f is depends on the shape of the lens. It depends on what the lens is made out of. It's like the concept of resistance. It's something you could calculate from the shape of the material, but as far as images are concerned, what you need to know is what it is. Okay, now this is for a lens. Mirrors have the same thing. If you have a mirror that is concave, curved like this, and you have light come in, it will bounce, and if you make the curvature right, it'll all concentrate at one location. You can concentrate light with mirrors just as well as you can with lenses. And again, there is a point where all of those rays cross, which is called the focal point, and it's a distance f from the surface of this curved surface. Now, in this case, because angle of incidence equals angle of refraction, you can figure out that if this is the surface of a sphere, this distance is about half the distance to the center of the radius of curvature of the sphere. So if this was the surface of a 2 meter radius sphere, the focal length would be about 1 meter. Again, that's not the sort of thing I'm going to focus on in this thing. I want to just say this is another parameter that depends on the shape, and it's something that's useful for understanding where images show up. Now, in these cases, the surface actually bends things and makes the rays actually cross. Other objects don't do that. Here's a lens example. You have light. Here, instead of having a convex lens like we had, say here, we had a concave lens. Things curve the other way. So now as light approaches this, it's bent away from the axis. So it goes up here and down here. So this thing doesn't concentrate light, it disperses it. But even in this case, there is something we can call a focus. That is, if we look at the light after it's gone through the lens, it looks like it's all coming from a point. It's from a point behind the lens, but it's still there. You can still geometrically define it. We can still call this the focal point, sort of, even though no light ray, except the central one, actually goes through it, because it's where the light seems to come from. And in this case, we can still define a focal length. But by default, to distinguish it from the other case, this focal length will turn out to be negative. Why would you want to do this? We'll see some examples of that. Same thing with mirrors. If you have a mirror that's convex, that is curved outward, you can disperse light. And in this case, again, you can track all of those rays back to a single point, that's called the focus, and define a focal length, but again, the distance is negative. Now, just to go back to this, notice in this case, we have the light coming in from the from the left, and the focal point is to the right. So we call this a positive F. In this case, the light's still coming in from the left, but now the focal point is also to the left, so we'll call the F negative. That's just how it works, and that's how it's been done. You might have other opinions on this. Deal. Anyway, so this is a very specific situation, though. We're talking about how light on parallel rays gets concentrated or dispersed. That's not entirely what we care about. What we care about is we have an object that is of some size that's emitting light in all directions. And then that light hits a lens and then gets concentrated back down here. This isn't the exact same thing we talked about. This has more complicated. You have light on different trajectories being concentrated. Now, a properly designed lens will also concentrate light from a nearby object, and it will produce a place where all of these light rays cross. It's not the focus. The focus is here. It's where parallel light rays will cross. This is a different point in space, but it still exists if you've built the lens properly. You don't have to. This place, if this sort of situation exists, where light from an arbitrary object is concentrated at one point, or again, a light source at one location produces a bunch of rays that converge at another point, then only a light source there can produce a signal there. Similarly, if you look at where, for example, this is a picture of a person, the light from the person's head all ends up here. The light from the person's feet actually ends up here. This is, again, a place where you can put a detector element and figure out, put a detector element like a CCD or a retina to make an image of this. So this is called an image. This place where all the rays converge is the place where there is an image of this object. And because that's a real point in space where the rays are really converging, we call that a real image. Now, if we look instead at a diverging lens, something that spreads things out, it turns out that, of course, doesn't make a real image because the light doesn't converge. But if we have a source of light, like, say, this flower, the rays get bent in such a way that if we remove this thing and track them back, they all look like they came from a smaller flower that was here. There's still an image in the sense of after passing through this, the light rays seem to come from a different location, a different source. But we can't put a detector here to see that because the light rays don't actually converge here. This is what we would call a virtual image. It's where the light rays after the lens seem to come from. Now, this is less useful for where would you put your detector element. Like, you can't put your retina in front of this lens. That just doesn't work. But it is useful for understanding how to combine these sorts of lenses with other optical elements. This is now, if we have this lens in conjunction with another lens, the second lens gets the light as if the source is here. So this is relevant for understanding how to combine optical elements. Okay? Cool. So there are a couple of key parameters we want to know about this image. And those parameters depend on both the size of the image, which is conventionally given in terms of this parameter H0 or H object, and where that object is relative to the lens, which is this distance D0. So we have an object of some height, H0, and some distance D0 from the lens. What's relevant for what we see or what we detect is the size of the image, which is HI, the height of the image, and where that image occurs, DI. The DI is very critical because this is where we would need to put our detector element or need to consider when we're considering other optical elements. So we want to know how far in front of the image, the lens, the image is. That's important. Now, in practice, we don't necessarily care about the absolute value of HI. What we're more interested in is what's the ratio of HI to H0. That's what's defined as the magnification, which is commonly known with the letter M. Now, this is just how big the image is relative to the object. Now, if, for example, you want a microscope, you're going to want a big magnification. If you want something that could take a picture of a person in say a camera, you'd want a small f. But these are two basic parameters that you care about when you're building optical systems. And the question is, how do we figure these out? Now, again, this is something that could be an arbitrarily complex question because, and indeed, if you really want to build a proper lens, you can make it really complicated because you want it to see particular objects at particular distances really well. So this is why there's an entire field on optics that we're not getting into. Just to get a sense of how things tend to work, we're going to work in what's called the thin lens approximation. This is a case where the geometry is relatively simple, and I can write down formulas that you can just use. The thin lens approximation allows you to basically relate those parameters we're looking for to things like the focal length relatively straightforwardly. The assumptions behind a thin lens are as follows. First of all, the lens is thin. That is, we don't really have to care that the lens has a finite width. That part of it doesn't really matter. So we can just say the focal length is the distance from the lens rather than from the center of the lens. The second approximation is that light passing exactly through the center of the lens isn't deflected much. That's a very vague statement. Light passing through the center of a lens will be deflected by some amount. But the idea is we're going to work in an approximation where we can ignore that. Now, again, if you're doing proper optics, etc., that's a thing you have to assess. But for the purposes of getting where images typically are and how they often are located, this is a useful first step approximation. Okay? It's like assuming a frictionless surface. It's just useful for understanding how things work. Okay, so what we're going to look for are a couple of equations that can tell us both this distance and the magnification. Now, again, the book just gives you those. And this is a case where I feel honor bound to tell you where they come from. And it turns out they're not that obscure. Just from those previous assumptions about how these lenses work, you can figure out these things called the thin lens equations. They're not mysterious. And so I do want to show you where they come from so that you have some idea of why they're useful. So what we're going to look at is this simple situation where we have an object, a person, and a lens that produces a real image. And we're just going to ask where that image is given a couple of these rays. So again, we have rays that go in different directions and all converge at some point. And again, we have a person that's a height h0, a distance d0 from the lens. Okay, so how does that work? Well, let's do it. Let's first consider the simplest ray, the one that goes straight through the center of the lens. Well, if we focus on that one, that was ray 2 in the previous figure, we got a pretty simple geometry. We have a straight line that goes from up here to down here. Now, that already tells us something. Since this ray is a straight line and the axis of the lens is a straight line, we know this angle here, which I'm calling theta, and this angle here is the same theta. We have a triangle here made up of the person, this length, and this ray. And we have another triangle here made of the image, this distance, and this part of the ray. Since this angle and this angle are the same, these two triangles are similar. What that means is that we can relate the ratio of lengths here to the ratio of lengths over here. Or if you like to think about it in terms of tangent functions, the tangent of this angle is the ratio of the height of the object to this distance d naught. That's just what it is. But it's also, because it's this angle, it's the ratio of the height of this image to the distance to the image. So we can say tan theta is h naught over d naught and also minus hi over di. Now you might wonder, why is the minus sign there? The reason the minus sign is there is because by convention, a height below the surface is taken to be negative. So an image that's upside down or inverted is taken to have negative height. This is a convention for people who are hundreds of years old. But what it means is that that magnification, which is the ratio of these two things, is also the ratio of these two things with an extra minus sign because of how h was defined. So the magnification is not just the ratio of the heights, it's also the ratio of the distances, which is kind of interesting, but not terribly useful yet, because we don't know this distance yet. But we can get that. We can get that by considering the other ray, the ray that leaves this object on a horizontal line and gets bent down. Now this ray, since it was horizontal, gets bent by the lens and passes through the focal point. That's the definition of the focal point. And then it keeps going straight until it hits the image. Again, this is where all of those lines cross. So it has to pass through there as well. So again, though, we have a pair of similar triangles. We have one triangle that is person h tall and a focal length for the leg. And here we have something that's the height of the image tall and this distance, which is the difference between di and f. So we can define another angle here, phi, if you like to call it something. The tangent of phi is h over h naught over f, or hi over di minus f. The thing is, so we have another relationship between the heights. Now it involves the focal length and the distance to the image. Now, that magnification equation also allows us to turn both of these h naughts and hi's into d naughts and di's. Basically, you divide one of the two sides of the equation by, say, hi, and then you get h naught over hi, and you can replace that with d naught over di, or however you want to do it. You do that substitution, do a whole bunch of algebra, which I won't do here. If you're interested, I'm happy to do it. And you get this relationship, that 1 over the focal length is 1 over this distance, the distance to the object, plus 1 over the distance to the image. And this is just a version that looks nice and symmetrical, so people like it. And notice it makes sense. 1 over length equals 1 over length plus 1 over length. All the units match. So this is what's generally called the thin lens equation. And what it means is, if you know where the object is and you know the focal length, both of which are things you should know, you can figure out where the image is. You just can rearrange this expression, get 1 over the distance to the image is 1 over the distance, 1 over the focal length minus 1 over the distance to the object. And then you could do 1 over that to get the actual expression. Okay? And then, because you know where the distance to the image, you can use the magnification, this equation, to figure out what the magnification actually is. So you can figure out pretty much all you want to know from reasonable things to have, namely the distance to the object and the focal length. And that's what few of your problems are basically asking you to do. And one thing that's interesting about how this expression works is that we derived it for the specific case where the person is here and there's a real image over here. But this equation is more general than that. For example, if there are some quirky things that happen to this equation when we make the object too close to the lens. See, 1 over the distance to the image is 1 over the focal length minus 1 over the distance to the object. Now, if the object is far away, d naught is big, then di is positive and everything is fine. But if d naught is smaller than f, then 1 over d naught is bigger than 1 over f. So this is bigger than this, and di becomes negative. That's actually okay. Because what happens in that case is the image now appears on the other side of the lens. The place where the light rays appear to converge is not a real point in space anymore. It's an interpolation of the trends that exist behind the lens. This is where this is the virtual image, no longer the real one. So if di is negative, you have a virtual image. And also because m is minus di over d naught, m is now positive. It turns out that virtual images are not inverted. They appear at the same size. So if you have an object here, this time it's just a little arrow, you track the light out, they're diverging from each other, but you extrapolate back, you get an image that's bigger than the object and appears to be further from the lens. This is how you make a magnifying glass. You see, instead of seeing a small thing, you see a big thing. And if you have more generally a diverging lens like this, you can also get virtual images, in this case, because f is itself negative. Even though this object is at a real location, and so 1 over d naught is positive, 1 over f is negative, so this thing will be negative, and the image will therefore be somewhere else. So you can use these equations for any lens. You just have to know that if di is negative, it means you have a virtual image. And you have to remember, if you have a diverging lens, that f can be negative. And it goes even further than that. This same expression can be used for mirrors. If you have a mirror with a real focal length, like a converging mirror, that focal length, and you have a real object, you can calculate the location where all the rays cross, which is where the real image would be, using this same expression, and you get the same expression for the magnification. So this particular expression is very useful. It's very general. And as long as you can keep track of when the focal length is positive and negative, or where the image distance is positive or negative, you can use it in a variety of different contexts. And it also means there's particular relationships about the size and reality of images under different situations. And what the next video will focus on is looking into that, trying to do a few different problems, some of them conceptual, some of them calculational, to get a sense of what this expression actually tells us about the specific types of lenses it applies to. Thank you all for your time.